Welcome, dynamic students. We're continuing to use work energy principles to uh, allow us to more easily solve uh, e for equations of motion and other variables we need to know for particle motion or bodies moving in a way that we can treat them as particles at their center of mass. So again, stipulations for this is we don't have any body rotation, so the bodies are moving in just rectilinear or curvilinear motion. It's translating. So in this case, we have somebody who's definitely moving on a curvy path. We have a skier who's going to descend a slope that whose vertical section can be described parabolically. So the skier's height y for any distance x away from the low point of the slope, maybe he's going down into a gully or something, is x squared divided by 256, and I believe everything is in feet. So y will be in feet. The skier weighs 120 pounds, so remember, if we need his mass, we have to divide by gravitational acceleration in feet or inches as we would have it, and we'll get a value of mass in slugs, the British mass unit. So we're given a starting position. This is good. All of our potential energy expressions require, an initial position. And so this would be 100, y equals 100, x equals negative 160, skis down the parabolic slope. And somebody wants to know, what is the force of the snow on the skier's skis when they reach point O? Why would we need to know this? Maybe this is a competition ramp, and we need to make sure that the snow base is properly compacted. If we've had a thaw and it's really mushy, and the force of the skier is too high, his skis might bury themselves in the snow and he might go cartwheeling and have an accident or an injury. So the snowmaking and snow grooming might need a number that they're going to react to make sure that the guy is okay. So that might be one practical application for knowing what the normal force is that he's going to have. So this scenario definitely suggests a tan normal coordinate system, since we're moving on a known path. So we're just going to plan to set up for understanding acceleration and velocity in terms of tangent to his parabolic curve, which will be given by the first derivative of that curve. That'll be the velocity, the tangent direction, the slope, and then acceleration using our normal, our typical tangent normal coordinate system. So we know one thing that's really important in our tan normal is the radius of curvature, which is like the radius that we would have for polar coordinates that we're going to multiply, especially to get normal components of acceleration. So because we've got a curve and we may not have remembered radius of curvature general expressions, we went ahead and looked up what is the expression for radius of curvature of any function. You can just look this up in a math book or in on a good math tutorial on the internet, and we find that it is 1 plus the square of the first derivative all to the 3/2 power divided by the second derivative. This is something we could probably all derive, but for the point of this problem, we're just going to use this expression. And this is, of course, dependent on the point. The radius of curvature is probably much bigger up here, smaller down here. And we only need to evaluate it at x equals 0. And so we know that at x equals 0, we have a minimum. So at extrema, we've got a value of 0 effectively for the first derivative. So this will be ending up being 0. The second derivative, we've got our expression, our y double prime would end up being just, first derivative is going to be 2 over 256 times x. The second derivative will just be the constant 2 over 256. So that'll go into the denominator, and we can evaluate this expression and end up getting value at 0 is going to give us a radius of curvature of 128 feet. And feel free to check this, but that was something that I just went ahead and evaluated. Again, we would, if we needed to know this something about radius of curvature everywhere, we would have to be invoking this formula at every point in the motion. But as in so many cases in dynamics, there's only one point in time or space that we really care about. So in this case, we only have to know the radius of curvature at that point, and that's the point of interest right there at the bottom. Okay, he starts from rest, so maybe it's like a ski jumper starting. So his initial velocity is 0, his initial kinetic energy is 0. The work that's going to be done due to gravity to get him from that the starting point down to the point of interest is going to be the force of gravity, which is his weight of 120 pounds times the vertical distance traveled, so 120 pounds times 100. So our initial total mechanical energy is just the potential energy. When he gets to this point, he will have only kinetic energy. So we haven't been told that there's any frictional force. We're told there's snow. So we're just going to assume from the point of view of the magnitudes of the work and energy changes of the problem that any frictional losses of his skis on the snow are negligible. So kinetic plus potential starting equals kinetic plus potential at ending, or at our point of interest down here. So we've already set up to know that our starting total energy is our 120 pounds times 100 feet. And so now let's take a look at the components that will lead us to our potential energy, or excuse me, our kinetic energy when we get to the bottom here at point O. So we're in tan normal coordinate systems. Velocity anywhere in a tan normal system is going to be the tangential velocity in the tangential direction. Okay, so S dot is our tangential velocity. So we can use that as an expression in our kinetic energy for point 0. So we can say 1/2 m times S dot squared is going to be our total kinetic energy. We're going to invoke energy balance now. Say that that's equal to the starting potential energy. We haven't lost any. We have no other sources. So we have an expression for velocity at any time. Well, that's nice. Definitely at time 0, not at any time. Woo! Catch me there. One time. 1 point. We know the velocity at that 1 point. Okay. So how does that give me the normal force? Well, let's go invoke Newton's second law in the normal direction. So to do that, we're going to need an FBD. So here's a skier, and he's skiing along, and he's right at that low point. So he's got his weight acting downward and the normal force acting upward, and the two are collinear at this point where he's right down there at the bottom because he's not on a slope. So we can say the sum of the forces on the skier is equal in the normal direction, which is kind of vertically upward at that point O, and only at that point O, is going to be equal to his mass in slugs times his acceleration in the normal direction, dotted, or with a dotted into the unit vector for the normal direction. So normal force minus his weight is going to equal his mass times normal acceleration. So we can drop back to our expression for acceleration in the normal direction in a tan normal system, a coordinate system, and we know that that is S dot squared over our radius of curvature. So wasn't it handy to have S dot at the point of interest, because that indeed is our link to our normal force via the coordinate system appropriate expression for acceleration. So we used a force balance, we used an energy balance plus Newton's second law plus an expression for acceleration particular to the coordinate system, which makes sense to give us enough equations to solve for the unknown, to find and isolate and solve for the unknown we needed. So we have our S dot squared over rho, which is going to give us our AN acceleration in the normal direction of 50.27 feet per second. We know the skier's mass. We know we know gravity. So now we can solve for n with this expression. So we needed to get the skier's mass. He's 3.73 slugs. So that ends up here. S dot, we just solved for with our energy balance. We got rho from our general mathematics of radius of curvature, and we were given his weight. We know gravity. So the normal force is 308 pounds, more than double his own weight. So the snow needs to be in very good shape to keep him safe through his skiing path. Okay, last example of work energy problems, and this is a little bit analogous to a laws of motion, just particle kinetics problem that we did in an earlier lecture. We got something that's flying off a surface again. Boy, we got this safety problems. Always something isn't going to want to stay in a pathway we want it to. So maybe in this case it was supposed to be launching off. So we have a spherical surface or cylindrical. We're going to work in 2D, so it doesn't really matter to us. We'll say it's a cylinder, and you've got a little ball on the top of the cylinder. And it's going to roll down the side normal to the cylinder axis, and it's going to pick up speed. It's going to accelerate in the tangential direction with gravity operating on it in that direction. And at some point, we're told it's going to go flying off the side of the cylinder. And somebody wants to know at what angle relative to the normal does it leave the surface? I guess it's rolling on a sphere. So we gave it a nudge to get it to where it was in equilibrium here. So we gave it a nudge, but not enough to really give it any initial kinetic energy, but just enough that gravity started operating on it. So at some point it goes flying off. Now, goes flying off the surface. We're going to start by translating that physical scenario into something meaningful to us. When something leaves a surface, and we focus on the point that it's departing. At that point, it has not stopped traveling on, in this case, a circular path. It's still going on a circular path, but it's not in contact with the surface anymore. It is dr away from this circular surface. So because it is not in contact, normal force is 0. So we can translate departs the surface as, I need to find where, in terms of theta L, does the normal force go to 0. And solve for that in terms of everything else I know. So what else do I know? We're going to solve for it in terms of just the stuff, the information we're given stuff. Data input, mass m. We know it starts vertical. It's operated on by gravity. Okay. That's all we know. Okay, so let's start with the coordinate system. We're going to say it's sliding down the side of a sphere. So if I look at a sphere in 2D and I draw a 2D section through a sphere that includes its center point, it's going to look like a circle. So we're looking at the one vertical section through that sphere that includes a point that's straight up, because it says we start at the top and we're showing the center. So effectively we're looking at a circular cross section. So it could have been a cylinder, honestly. So we're in polar coordinates. We're talking about a circle. So let's write an expression for velocity and then acceleration for this particle in polar coordinates, because then we can start relating to forces in radial and theta directions, which is the same as radial and tangential, given that it's a circular path. Okay, so v sub p, which is the velocity of that particle. Notice it could have been a bigger particle. We're going to treat it as a single particle at its mass center. Is r dot, in the r hat direction plus r times theta dot in the theta hat direction. Okay, when it reaches theta L, it's not gonna follow this path anymore, but we don't care what happens afterwards. We're not working on that dotted line for this problem. Although, again, if we knew what the velocity was, which we'll probably end up with an expression for it at this point, once it leaves the surface, we could write another equation of motion at the point where there's no more normal force and it's just heading off wherever. So, but that's not part of the scope of the problem. So, other things that we know until we reach that point, we know that it's traveling on this rigid circular path, a rigid sphere, so r dot is 0, r double dot is 0, the radius is not changing. So at the very least, we can get rid of that. So here's our expression for velocity at any point. Why did we want that? Because now we can write an expression for kinetic energy. So let's look at the work that gravity will have to do on this particle to take us from its starting point up here to wherever it departs. Well, gravity is going to have to move it down this far. So if we write an expression for the vertical height at the departure point and subtract it from the starting point, apply the work of gravity mg over that vertical distance, we will have what's effectively the potential energy of our starting point, or the work done by gravity to get us to our flying off point. So we can write that here, mg of the total radius minus r cosine theta. It's going to give us our total work done by gravity, which ends up being, which we can then equate to, ends up being this. Then we can write an expression for kinetic energy using the magnitude of our particle velocity at any theta. So square this, multiply by m over 2, put in the actual radius, capital R, of the path. So here's our KE and our PE. So here's our energy balance expression. We didn't see any mention of friction, so we can equate these two. PE equals KE. So we have one expression to relate things we might want to know. Okay. This doesn't tell us anything about when it departs. Remember, we've got to somehow get an expression that involves normal force, because that's what's going to tell us when we're leaving the surface. So, force. Let's go back and let's FBD the particle and start invoking Newton's second law with acceleration. So let's start by just reminding ourselves what acceleration in polar coordinates is. So we've got the acceleration of our particle in terms of our radial component and our theta or tangential component. Our double dot 0, our dot is 0. So we just have our radial component of acceleration as negative r, which will be big R, times theta dot squared, plus our tangential component, which is r theta double dot, or tangential acceleration at whatever point. Okay, so we're going to equate this to the sum of the forces in the radial direction, and we're going to equate this to the sum of the forces in the theta or tangential direction. So let's do that force balance, and let's get an FBD to help us. So here's an FBD of our particle, our little ball. We've got the normal force acting upwards. We've redrawn that angle theta using basically the principle of vertical angles, and so we can relate the normal force to the gravitational force, its directions. So normal force is acting solely in the radial direction, and we have an mg cosine theta L component of the weight acting opposite to that. So this is our radial direction force tally. where we've put the radial direction as outward this way in the direction of normal force, ER, calling radial positive. And so we can equate that to, again, our radial acceleration in polar. So there it is, negative r, where little r is big R, in this case the big R of the sphere that the little particle is rolling down, and our angular velocity squared times the mass. So now we can see that we could look ahead and go, okay, at the point at which this little particle flies off the sphere's surface, n will be 0, and we will have an expression that relates theta L to angular velocity, and that might be useful to us in G. So let's see what else we have. We have in our tangential direction, we have mg sine theta L, which is that component, which is tangent to the sphere, is going to be equal to our tangential acceleration, our theta double dot. Okay, so now next step, we're going to allow the particle to depart the sphere, that's dr. So n goes to 0, and we end up with just our radius times angular velocity squared equals g cosine of this angle of travel. So now we can start substituting, going through our solution steps. So we have okay, tried to take a pause to erase some extraneous lines, and we didn't have a lot of luck with that. So now we're going to re-invoke our work energy, because we've got a great expression for position that corresponds to when we depart. We've said, okay, we've let the particle leave the sphere by invoking n equals 0, and so great. The angle is given by this expression. This does answer the question, but like we've seen before, that's a differential equation. I bet when they say at what angle does it leave the sphere surface, I bet they wanted some algebraic expression. Drat. Well, let's see. What's really hanging us up is this term. We'd really like an all algebraic expression for theta L in terms of mass and gravity and something like that. Have we seen this term elsewhere? Oh, good heavens, there it is right up here in our kinetic energy term. If we kind of did some manipulations with R for our convenience, so we can invoke our potential kinetic energy expression to solve for this term in terms of just mgr and an algebraic expression for theta L. So we're going to reorganize this equation so we isolate our r theta dot squared on one side, and we get this expression coming out of our potential kinetic energy rearranged, equaling r theta dot squared, and that of course is equal to our g cosine theta L. So we end up getting rid of this inconvenient time derivative there, and now we just have theta L, cosine theta L on both sides. So now we just do some algebra and say that, okay, our cosine of theta L is going to equal 2/3, so theta L is a single number at the end. So did we need potential kinetic energy? Did we need a work energy kind of expression to actually get an equation of motion that involved the departure point? No. We actually got that straight from our Newton's second law, one of our Newton's second law, a radial only. It's all we needed. The work energy really came in handy to make the math easier and to give us an easier expression. Turns out we didn't really end up invoking the tangential or theta component of our Newton's second law either. So Again, this was not like the previous problem where we directly applied work energy to solve for the very thing we wanted. This is where we used work energy to give us a second equation that rendered our Newton's second law differential equation of motion an algebraic. So we got our given number. It's at 48.2 degrees, so just a little past 45 degrees. It goes flying off. So, and it's a single number that doesn't end up being dependent on much of anything other than just the geometry of the problem, literally. So that is our last example of work energy definitions being used to solve for equations of motion and other points that we need to know in a particle scenario. Or body being treated, a translational motion of a body where we can treat that whole body as if it's a point at its center of mass. So the next topic that we'll cover in particle kinetics is impulse momentum, where we look at particle momentum changes as being the result of a force applied over a given time, the concept of impulse, and look at the unique ways we can combine that with kinetic energy changes to find out even more that we know, so that we will basically forge ourselves a couple more tools to make these equation of motion solution problems a little bit easier.